Welcome back to my channel Easy and Inspire. In today's session we are discussing about JK-Flipflop. Listen carefully. JK-Flipflop is nothing but modified version of SR-Flipflop. So before going to the topic, why we are going for JK? What is the problem in SR? So in SR-Flipflop we know if R is equal to 1, that is what? If reset equal to 1, then output is resetted. This is output. This is complement or inverse of output. So if R equal to 1, output is resetted. Okay. If S is equal to 1, output is set to 1. So reset and set conditions. S0, R0 condition is nothing but no change condition. And there is one invalid condition in SR flip-flop. We know this one and we have already discussed. So this is about SR flip-flop. And in this SR flip-flop, only two, observe here, only two conditions are there. That is nothing but reset and set. To get these two conditions, we have gone to D-Flipflop. Listen, if D equal to 0, output is equal to 0. That is nothing but reset condition of SR. If D equal to 1, output is equal to 1. That is set condition. So to get these two conditions, we have developed D-Flipflop. So there is one more condition, no change. If you want this condition using D-Flipflop, you can apply a negative clock pulse here. Then you will get no change condition. So these two are conditions in D-Flipflop. And to overcome the problem in SR flip-flop, here the problem is invalid. So this state is invalid. To overcome this problem, we are going to JK flip-flop. You need to understand only one point here. So JK flip-flop is nothing but modified version of SR flip-flop. So it is developed to overcome the problem. So here this is the problem. So to overcome the problem of invalid condition. Okay. So JK flip-flop. So full name is Jack Kilby. So named after an electrical engineer who invented this flip-flop. So it is also called as universal programmable flip-flop because so any other functions can be implemented using this JK flip-flop. Listen carefully. It is also called as universal programmable flip-flop. Very, very important point. Here J is called as preset, K is called as clear. Listen, J is preset, K is clear. So JK flip-flop. So in SR flip-flop, S is set, R is reset. Here S is nothing but J, R is nothing but K. So you need to understand very carefully. So S is nothing but preset or J, R is nothing but K or clear. So same as SR flip-flop, but names are different. So it is the modified version of SR flip-flop with no invalid state. We are developing with no invalid state. So we are making it valid. So listen, here in this JK flip-flop, J input is similar to set input of SR flip-flop and K is similar to reset of SR flip-flop. It is having two inputs, two outputs, Q, Q bar and one clock pulse. We people know, so clock is there means it is called as flip-flop. Without clock it is called as latch. So construction and logic. Here I have constructed JK flip-flop using NOR gates, NAND gates. So you can use either this or this. I am explaining the operation using NAND gates. Listen the operation. It is very, very easy if you understand. Okay, I'll explain. Okay. So I am taking 4 conditions to the inputs, J, K inputs. So 0, 0 first condition, 0, 1, 1, 0, 1, 1. So I have considered all the 4 conditions here, but I am taking like this. Okay. Clock. So in previous classes we have already seen what is a clock pulse. Clock pulse is like this, and always I am considering only positive going or rising clock pulse, but not falling. So you can consider either falling. So I am taking only rising clock pulses. So only when this clock pulse is occurred, then the circuit is activated. If this is occurred, the circuit is not activated. That is the condition here. Okay. My first condition is J equal to 0, K equal to 1. So I am taking the same here. J equal to 0, K equal to 1. Always clock must be 1, then only circuit is activated. Okay, if you observe this carefully, these two NAND gates are having 3 inputs. So this is 3 input NAND gate truth table. So this is AND, this is NAND. So don't consider these values. So this is, these two are 2 input NAND gates. This is truth table of 2 input NAND gate, 2 inputs output. Okay. So I have placed 0 and 1s here. We don't know the third value because these two are previous output values. So we don't know these two. Then consider these values here. 1 here, this one here. 2 inputs, 0 here, 1 here. 2 inputs. 0 and 1 to NAND gate. 0, 1 results 1. 1, 1. So just I'm removing this one here. 1, 1. 1, 1 results 0. Okay. So we know one input, we don't know the second input. If you observe this carefully, we know one input, we don't know the second input. So either 0 or 1, it results 1. Either 0 or 1 here, it results 1. Okay. This one I am taking here. 1, 1 to NAND gate. 1, 1 to NAND gate results 0. Please pay attention. First of all, I have taken 0, 1. So the same I have played here. 0 here, 1 here. So this clock here. Here 0, 1 to NAND gate results 1. 1, 1 to NAND gate results 0. One input is null. We don't know the second input. So either 0 or 1 second input, whatever it may be, it results output 1. So I have considered this one and I have placed 1 here. 1 I am taking again here. 1, 1 to NAND gate results 0. So output is Q equal to 0, Q bar equal to 1. So I have already mentioned J is nothing but S, K is nothing but R. Here R equal to 1 means reset pin is activated. So observe here, output is resetted. Please pay attention, this is very, very important. So R equal to 1. So Q is 0, output is resetted. Q bar is equal to 1. Okay, this is my first condition. Here I have considered only 2 inputs. So now I'll explain by considering the third input. Okay, let me explain. So now you got output values here. Just this output is 0. So observe here, this 0 is going here. So place 0 here. Here it is 1. This 1 is going here. So place 1 here. 1, 0, 1. Listen carefully. I am taking the output values what we have obtained. So 0 I am taking here. 1 I am taking here. So 1, 0, 1. 1, 0, 1. Output is 1. So this is 1. 1, 1, 0. 1, 1, 0 to NAND gate. Output is 1. So again I am taking 1 here. So 1, 1. So previous values don't consider. I am taking only blue color one. Blue color one. Okay. So 1, 1. Again consider this one here. Past value. 0 here. So 1, 1 results 0. 0, 1 results 1. Same values we got. So without considering the third pin, with considering the third pin, we got the same values. This is about first condition in JK flip-flop. Now the second one, that is nothing but J equal to 0, K equal to 0. I'll explain. Okay. So in previous case we got Q equal to 0, Q bar equal to 1. Okay, I am placing the same. So Q equal to 0, Q bar equal to 1. Okay. Clock is, so I am taking now second condition. So 1, 1 clock. J equal to 0, K equal to 0. So now previous output values, Q bar. I am taking Q bar here. 1. So Q 0, placing here. 1, 0, 1. See here 1, 0, 1. It results 1. So place 1 here. 1, 0, 0. 1, 0, 0. 1. So place 1 here. So now 1 1. So one input is known, second input is not known. So we can't consider these two. So consider the same past values here. 1 here, 0 here. So you can take like this or just consider 1. So I am taking 1 1. 1 1 results 0. See here, 1 1 results 0. So you can take this value. So 0 1 results. See here, 0 1 results 1. So you can consider this value or this value. So whatever it may be, you got the same. Okay. So similarly, I am placing Q here, Q bar here. Just pay attention. In this condition, I have taken my values and I have considered my past output values here. Okay. So in this way, you have to perform. So if you observe this one, so S R, S equal to 0, R equal to 0 in SR flip-flop is no change condition. Here is 0, 0. That is nothing but same no change condition or memory condition. If you observe, 0 is stored, 1 is stored. So no change condition or memory condition, same as SR flip-flop. So next one, J equal to 1, K equal to 0. Okay, just place the values 0, 1, 0, 1. What we got, I am placing here. For this condition, previous output values are these values. Q equal to 0, Q bar equal to 1. Place. So 1, when clock is 1, J equal to 1, so 1, K equal to 0, 0. So see, I am taking this one here. I am taking this 0 here. 1, 1, 1 to NAND gate. 1, 1, 1 to NAND gate results 0. Okay. 1, 0, 0. 1, 0, 0 to NAND gate results 1. So one input is known. See here, one input is known. So whatever the second input may be, it results 1. Listen, in previous case we got, in this condition we got 1 1. So we don't know the values. If it is 0, it results 1. If it is 1, it results 0. So I don't consider these values, just I have considered past output values. But in this case, one input is known. Whatever the second input may be, it results 1. So whatever the second input may be here, it results 1. So now place this one here. 1, 1, 1, 1 results 0. These two are my new values. So 1 here, 0 here. See, 1, 0. So S, R. Here, S is equal to 1. So output is set to 1. Same as SR latch or SR flip-flop. See, S is equal to 1. Here, reset equal to 1. Output is resetted. Output is setted. Next, fourth condition, 0, 0. So again, you have to prove this as no change or memory condition. Okay, let me explain. Place output values. Just I'm erasing, so I'm placing again here. Don't get confused. So these are my values. So for this condition, previous state is this one. So Q is 1, Q bar is 0, clock is 1. So JK both are 0 zeros. 0, 0. Okay. So this 0 I am taking here. This one I am taking here. 0, 0, 1. 0, 0, 1. Results 1. Okay. 1, 0, 1. 1, 0, 1. Results 1. So again 1, 1. We don't know the second input. So second input where is? So again consider 0 here. 1 and 0. 1 and 0. It results 1. Again this one here. 1 and 1. 1 and 1 results 0. These two are my new inputs. Because, so 1 and 1. So we know first input, we don't know the second input. So I am taking the previous values here. Okay. Again same answers, 1, 0 I got. So observe same values, that is nothing but memory or no change state. Okay. Now the very important one is J equal to 1, K equal to 1 condition. So you have to pay more attention here. Okay. Just I erased all this data. So I'm just placing 0, 1, 0, 1, 1, 0, 1, 0. Okay. For this condition, my previous outputs are 1, 1 and 0. Clock is 1, 1. So clock is applied here. J equal to 1, K equal to 1. Okay. So now I'm taking this previous value here. 1, 0 to here. So 0, 1, 1. 0, 1, 1. It results 1. Okay. See here. 0, 1, 1 results 1 here. 1, 1, 1 results 0 here. 1, 1, 1 results 0. Okay. So now one input is known. One input is known. So I'm taking one more color here. One input is known. Whatever the other input may be, it results. Please pay attention. One input is known. Whatever the other input may be, it results 1. See, one input is known. Whatever the other input may be, it results 1. Place this one here. 1, 1. It results 0. So you got 0, 1. So if you observe this carefully, output is changed. 1 is changed to 0, 0 is changed to 1. Okay. Again, pay attention here. Now, I'll take one more color. Okay. So now the same. So this is previous output values. This is my output values. Okay. Now these output values I am giving here. This 0 I am taking here. So this is very, very important case. Very, very important case in JK-Flipflop. This 0 I am taking here. So 1 is replaced with 0. This one. So see, this one I am taking here. So 0 is replaced with 1. 1, 1, 1. NAND results 1, 1, 1. NAND results 0. So it is 0. 1, 1, 0. 1, 1, 0. It results 1. It is 1. So one input is 0. Whatever the other input may be, it results 1. One input is 0. Whatever the other input may be, it results 1. Now I am applying this input here. So 1, 1. 1, 1 results 0. So it is 1. It is 0. So if this operation is performed, if the same operation is performed for the above conditions, you will get the same, because for the first case I have already explained by taking only 2 inputs and output again I have applied to input here and I have observed the operation and you got the same. So listen. So in the first condition I have applied the output to inputs in the first condition. So without taking the third input, by taking the third input, you got the same values 0, 1. So similarly, you can check this one also. Just I have explained only one. But in this condition, if the output values are going to input, then output is changing like this. See, 0 to 1, 1 to 0. Again you get 0, 1, 1, 0 like this. That is nothing but toggle. So 1 is here reset, set, reset, set. Like this, state is changed. That is called as toggle condition. Very, very important condition in JK-Flipflop. In SR-Flipflop, so that is invalid. But in JK-Flipflop, this condition is called as toggle condition. Okay, this is very, very important. So just place these output values here. So and check it. So in these two conditions, you will get the same values. I have explained this one. But in this condition, you will get different values. So this is called as toggle condition. This is the truth table. So just I have derived this truth table from the above operations. So if you observe the above operations, so 0, 0, 0, 1, 1, 0, all these cases are same as SR flip-flop. But 1, 1 condition, this is different from SR. In SR, 1, 1 condition is invalid. But in JK flip-flop, 1 1 condition is toggle condition, because if it is 1, it is 0. So it is 1. Next, it is going to change as 1 0. Again 0 1. Again 1 0. Like this, it is going to be changed. So this toggle condition is going to be continued. So this toggle condition is going to be continued only when clock pulse is applied. See here, only when clock pulse is applied. If you stop this clock pulse, then it remains in no change condition. This is very, very important point. So toggle condition is going to be activated only when clock pulse is activated and JK must be 1. Then only toggle is activated. Okay, this is the truth table. So here JK both are zeros, no change state. 0 1, reset pin is highlighted because SR, right? So reset is highlighted, output is resetted. Set is highlighted, output is setted. See, reset, set and toggle. So toggle is activated only when JK must be 1 and clock must be applied. So this is the truth table. Next we'll see characteristic table. So this is the characteristic table. So JK input, clock pulses, and Q of t means present state, t plus 1 means next state. Okay. So we know JK both are zeros here. So 0 0 means that is no change or memory state. Okay. So if present state is 0, next state is also 0 because no change here. If it is 1, present state is 1. Again, next state remains in 1 because no change. Okay, J0, K1 in these two conditions. See, in these two conditions, J is 0, K is 1 means reset pin is highlighted. Whatever the present output may be, it is going to be resetted in the next state. See, 0 is resetted, 1 is resetted. So whatever the output may be, it is going to be resetted. Here, in this condition, it is set because J is S, K is R. Output is set to 1. Whatever the present output may be, it is set to 1. So this is about JK flip-flop with 3 conditions, same as SR. But the last one is very, very important, toggle condition. See here, 1 1 condition. So 1 1 condition, here J is 1, K is 1. So if present state is 0, next state is going to be 1. If present state is 1, next it is going to be 0 because it is toggled. So it is nothing but resetted here. Next state setted, again resetted, again setted. So like this, the output is toggled. See here, toggling means switching between two states. Here states are reset and set. So reset, set, reset, set. Again set, reset, like this toggling. Conditions for toggle are both J and K must be 1 and clock must be present. Listen, both J and K must be 1 and clock must be given to the flip-flop. Then only toggle condition is activated. So very, very important. So just observe timing diagram. I have taken two inputs J, K, clock. So pay attention here. So my consideration is always clock must be 1. So in these conditions only output is changing. So in the remaining conditions output is not changed. Okay. Okay, always I am considering positive going or rising edges. So like this, all the positive going edges. So first positive going edge. So this is the positive going edge. So see, this is S, this is R. Okay, here S is 0, R is 1. So R is highlighted, so output is resetted. See, output is resetted, so it is 0. Actually, it is 1. Next, at this point, observe. So S is 1, R is 1. See, S is 1, R is 1. So both are 1. So output is toggled. 0 is toggled and it is going to 1. See, output is toggled since J is 1, K is 1. So observe. next output is toggled and continued here. So in this, at this point, so J is equal to 1, S is equal to 1, so R is equal to 0. See, at this point, S is 1, R is 0. If you observe this, it is setted. So already it is in set position, so it is going to be continued. Please pay attention. It is setted. Setted means 1. So if it is 0, it is going to be 1. Already it is 1. So it is going to be continued. Again, here at this point, J is 0, K is 0. Both are zeros. So it remains in no change condition. Again, continue. Again, 0, 0 here. Continued here up to. Again at this point, if you observe here, so J is 1, K is 1. Both are 1. So JK1 means toggle condition. So 1 toggled goes to 0. Again here, both are 1. So 0 toggled goes to 1. Again toggled here because both are 1s. 1, 1. Again toggled. So you can observe toggling condition here clearly because JK both are 1 and clock is applied. So my condition is positive edges. At every positive edge, it is toggled. 1 is going to 0, 0 is going to 1. So this is timing diagram of JK flip-flop. So we can conclude that JK flip-flop is same as SR flip-flop. But the last condition, 1-1 condition is changing to toggle condition. JK flip-flop is having a small limitation. I will explain the small limitation and I will discuss why master slave JK flip-flop is invented. So because to overcome the limitation of JK, master slave JK is invented. I will explain this in next class. Thank you.